All right, thank you. Yeah, so title of today's talk is Wired for Safety. What we're going to talk about is control systems. We're going to kind of dive into a couple of different incidents, and at the end, we're going to talk about a cool tool that I built. So a little bit about me before we start. Um, my name is Jace Powell. I'm a security architect for Fortress. We work in the critical infrastructure vertical. Um, my background, I've got certifications and CVs and stuff, but really what I think is more pertinent here is my experience in the oil and gas industry. So before I got into cybersecurity, I worked as a roughneck and roustabout. Did a lot of repairing and maintaining some oil production systems, right? And that includes some OT equipment, some physical equipment that accompanies it. I also spent some time as a safety manager where I investigated industrial accidents and injuries and near misses and things like that. And I really saw firsthand the impact that industrial accidents can have on people, right? We're losing time at work and money and really sometimes food off the table. So it's still something I'm passionate about today. So in 2005, one of the worst industrial accidents in modern history here in the U.S. happened. There's a refinery on the Gulf Coast of Texas, in a city called Texas City, that experienced an explosion. There were some trailers that housed contractors and employees. This explosion killed 15 people and injured 180 others. Left a lot of people with lifelong injuries too. So really a bad thing. Took what does it say here? $1.5 billion to repair and rebuild the refinery. The company that ran the refinery was also hit with an initial $20 million fine. They actually didn't remediate all of these issues, and they got another $50 million fine slapped on later. So, but one of the core underlying themes you'll see here is really just a lack of safety culture. During the day of the incident, the facility, actually, I'll back up a little bit. The facility itself had been down and not operating at full capacity for at least a couple weeks. And employees were pulling 12-hour shifts, 7 days a week. Everybody's tired. During the actual incident that led to the explosion, they were doing a process restart, which is always kind of the most dangerous part. Is when things are spinning up and you're trying to get levels right, and once everything's stable, things tend to be a lot more safe. So here's a picture of the explosion. You can kind of see, looks like little Tonka trucks there, right? Those are full-size excavators and backhoes and things like that. That's where those trailers were at the time. So absolutely a devastating incident. Just for some bigger context here too, the explosion blew out windows 5 miles away. The explosion was heard 40 miles away, and it registered on the Richter scale. So it was a very large explosion, as you can see. Ironically, the explosion happened as employees were returning from a luncheon where they were celebrating 30 days without any safety incidents. So the Chemical Safety Board did a really good video on kind of the root cause of the explosion. This is a screen cap from, well, circled there in blue is the same site here that's kind of a debris field at this point. So you can kind of see where the trailers were at the time. I do want to lay some foundation and clarify first off, this was not a cybersecurity attack, okay? This was not conducted by an attacker or insider threat or anything like that. It was completely an accident, but we're going to use this as a case study to understand what a malicious attacker could do, right? Because they're going to try and have these same impacts using kind of some of the similar techniques. So down in the lower left corner, that's about a 170-foot tall tower. It's called a raffinate splitter. This is designed to refine some chemicals. Actually, the chemicals are very volatile. This is the stuff that they put into gasoline to make it more explosive. Or not, I'm sorry, to raise the octane. It is more explosive, right? So this is a hazardous chemical to work with at this point. circle here in red, there's a valve that on the left side, that's the base of the raffinate splitter. So the fluid's supposed to be coming out of there. Well, this valve was closed, and it was not made known to the process control operators. Here's a view of the base of the raffinate tower. So you've got this, they call it a sight glass, and the idea is you can see the fluid level with your eyes. Right next to that, there's a level gauge, and typically it should be around 6 feet. During this hazardous process restart, the unofficial SOP was to raise that level to 9 feet, which is the top of the sight glass and the top of the level monitor there. That level monitor would send a signal back to the control room to let them know what the level was. And again, this is a screenshot from the Chemical Safety Board's video, which is excellent video. There was also a high level alarm in here, and if you've ever taken the back off a toilet and you've seen the little ball float, that's kind of the same mechanism, right? In this case, it's actually a metal ball. Unfortunately, as the levels rose because that valve was closed, this ball valve was not inspected and it didn't work. No one got the alert that levels were high, right? So that's one failure of a digital sensor there. Fast forward a couple hours, and this tower, again, only designed to hold about 6 feet of fluid, rose up to above 100 feet. And at the time, not really pictured here, actually it kind of is at the base, that cubic structure there, that's a heater, right? And it's heating this fluid up very hot, and it's just building up. At the very top of this raffinate tower, there's a gas line that comes off, right? And this is designed to, separate the gases, and that's processed somewhere else. This fluid's rising, and again, no one's taking note. There's no high-level alarms, nothing like that, and the fluid overflows into that gas line. At that point, there's a couple safety bypass valves that are opened. Unfortunately, they weren't connected to the control room. They were just manually activated systems, so no one really took note that, hey, like something's wrong. And this fluid backs up into actually what's supposed to be a safety device. So this is called a blowdown drum. It's designed to vent gas into the atmosphere in the event that something goes wrong. It's not really designed to hold fluid, but as you can see, it's filling up with fluid, and eventually it turns into a fountain, basically. So this is shooting very hot, highly volatile chemicals all over. And the chemicals obviously are very, very hazardous, but there's also a vapor cloud that develops over the pad of the refinery. And it spreads out. Again, on the left side there, you can see the trailers. It might be kind of hard to see, but up in the middle, there's a kind of a little blue rectangle. And that was a pickup truck, a diesel pickup truck that was idling. There's a couple employees in there taking a break. And the vapors got sucked into the engine, into the intake, and caused essentially a runaway condition, right? So the RPMs are ticking up, and the employees notice something's wrong. So they get out and run away. RPMs continue to climb in the truck. It backfires, and that's what kicks off the explosion. And yeah, again, it was pretty devastating. So I mentioned the Chemical Safety Board. They were one of a few organizations that did a root cause analysis, and they kind of made this hit list of kind of the more high priority things that went wrong, basically. It was just one of those instances where the stars and the moon lined up just right, and it led to this incident. We're going to focus on the first one there, the failure of sensors. Really, there's 3 sensors that failed or did not operate correctly that led to the incident. The first one, it was next to the sight glass, right? It was that vertical gauge. What happened is it hit 9 foot, kind of as they expected, but as that fluid continued to rise, the gravity of the liquid in the tank changed, and that actually sent a false reading to the control system operators because it looked like the levels were actually going down. So at the time, they thought everything's fine. We're in good shape. We talked about the high-level alarm, second one that just completely failed to operate, and then the blowdown drum, the thing that vented or shot that fountain up. That also had a high-level alarm on it, and it also completely failed to operate. There were some other major contributing factors. The control room operators didn't really have the visibility into the system to tell, this is what's coming in, this is what's going out. They had the numbers, but they were on two different screens, and it just wasn't intuitive. Alert fatigue was another issue. If you work in the SOC, you can relate to that. They have these same issues in control rooms as well. So let's look at this from an attacker's point of view, right? Let's use this as a case study. Obviously, this is a worst case scenario, mass casualty event, destruction of the facility. If an attacker wants to cause an impact on an OT system, the way they're going to do that is to manipulate some of these Purdue level 0 and level 1 devices like sensors and actuators and valves and things like that. Stuxnet, right? If that's on your bingo card, you can check it off. You're welcome. But Stuxnet actually spoofed RPM sensors, right? Because they're spinning the centrifuges fast. But they spoofed the sensor values to the control room operators to make it look like everything was normal. The cybersecurity industry really doesn't monitor down at the process control level typically. We tend to focus on network security monitoring and say, okay, well, we can detect lateral movement and things like this. And as an industry, we tend to stay away from process telemetry. This is a great chart from Mandiant. Basically, the further down you move in this on these Purdue levels, the greater the severity of consequence of an attack. And that leads us to control loop compromise, right? I originally read about this in a paper from Joe Slowick, who discussed the concept of an integrity attack, right? That's where an attacker compromises the integrity of a control loop, causes it to fail in a way that causes some physical harm. I kind of prefer the term control loop compromise because, in cybersecurity, we have these incredible tools that we built, right? We can detect, commands being run on any machine, lateral movement, any anomalies, right? But we haven't really applied those detection capabilities to something like a control environment. So that's kind of what I set out to solve is how can we use detection engineering principles and actually help apply it to other areas, right? Especially ones that overlap with cybersecurity. MITRE does a really good job of breaking down some of the different techniques that attackers use. Kind of, in my opinion, really the Mac Daddy of MITRE attack techniques is loss of safety, right? T0880. That's loss of safety. And attackers are going to use these example techniques under really ultimately to try and cause a loss of safety. And that's what we want to prevent. So the question is, how do we defend against this? Again, MITRE nails it with their mitigations here. Having redundant components, mechanical protection layers are in use to varying degrees. Safety instrumented systems are a thing. Unfortunately, a lot of the SIS implementations we see, they run the safety instrumented systems on the same network as the control system. That's kind of not the purpose of a safety system. It should be completely segmented, be able to operate on its own. But we're making progress. And we talked about the bottom two here. Network security monitoring really doesn't get into process telemetry and things like that. So we've always focused on trying to prevent access, but we don't really have any tools to keep things safe in the event that there is an intrusion. So that's where I came up with the concept of what I call OT safe. So it's a Python-based framework. really what it allows you to do is build a Pythonic representation of your control system. So there's Python classes for sensors and controllers and actuators and HMIs and engineering workstations and even some non-cyber assets too. Pressure vessels and tanks and things like that. So pretty cool stuff there. So the idea is you build this representation of your control system, probably try and focus on one component at a time, one control loop at a time. And then from there, you can ingest PCAPs and really kind of bring your system to life and say, okay, this sensor is recording these values. And you can even listen on a local port. And right now it only supports Modbus, but the idea, again, is that you can feed in process telemetry into this system. From there, you can do things like build detections for unsafe conditions or integrity attacks, and really the use cases from there are pretty wide open. This also allows us to control for things like insider threats or sabotage, which, again, we don't really have a way of mitigating for this. So the Oldsmar water instance is a good example, right? Allegedly, an attacker raised the sodium hydroxide level to unsafe conditions. Well, why was the attacker allowed to do that? How come that didn't trigger some kind of a bigger alarm or an automated response or something like that? So yeah, a little bit about OT safe. Again, the core library is written in Python. There's a CI/CD pipeline, so if you want to build detections and test them, and you have PCAPs, it's all kind of included there. There's some other components too. Detection can be built in YAML or just pure Python. I've actually got a Python example here that we'll touch on coming up soon. But before we do that, we're going to talk about another incident. So this one's a bit more recent. It was a few years ago. There's a marine port in the southeast Florida area, Miami area. There was a large container ship, the big shipping boxes, the Connex boxes. It had docked in this port, and it was being unloaded by a ship-to-shore crane, right? So they pick up the Connex boxes and put it on a truck or on the ground or forklift or whatever they do with it. There was somebody from the parking lot, the employee parking lot, that hopped on the corporate Wi-Fi network. And unfortunately, they didn't have network segmentation, so their OT network was accessible from the IT network. And basically, what the attacker did was they just did a replay attack and sent a crafted Modbus packet that caused the crane, this Modbus command caused the crane to release. And typically, you would only do that if you're setting it down. The attacker replayed that Modbus packet and released the clamps from a crane in midair, and caused the shipping container to come crashing down. Luckily, nobody's hurt. It was definitely a close call, big investigation, and all that stuff. But it could have been a lot worse, right? Especially knowing that sometimes, in those shipping containers, there are hazardous chemicals and things like that. This picture, by the way, was not from the incident. This is just one I found on Google. So let's think about how we can use OT safe in this scenario, right? There's obviously quite a bit more complication to a system, but when you boil it down to the fundamentals, you've got this ship-to-shore crane, and really you've got two components you care about, right? You've got the status of the clamps, and you've got the load pack or the load sensor on the crane. This tells you how much weight is being suspended by the crane, and every crane operator has them. They're required. But really, those are only the two components that we really care about. And think about what your detection logic would look like, right? The clamp should never go from closed to open when there's a load suspended. Pretty straightforward. So let's build a detection in OT safe and see what that looks like. So line 6, this is my clamp. Line 14, I've got my load sensor. Line 24, this is the same script. It's just cut for readability. Line 24, I'm just listening on a local interface. Assume it's got like a tap or some kind of a packets being sent to it. And then we just loop through it and listen. Line 28, that's kind of the extent of the detection logic, right? If the clamp's open and the value of the load sensor is, in this case, greater than 100, just an arbitrary number there. That from there, OT Safe also has alarms that you can raise. So, in this instance, line 32, we're going to raise an alarm and, follow-on actions from there, kind of more up to the owner-operator outside of the scope of OT Safe. So that's kind of a quick overview. A lot more to it than that. I've been toying with the idea of a digital lockout tagout system, which if you're not familiar, anytime, say, an electrician has to work on some equipment, right? They'll shut the power off, but then they'll put a lock on that switch, and only they have the key, right? And the idea is nobody can energize a system while they're working on it. So lockout tagout's pretty common thing that you see in the industry. It's pretty interesting to think about how we can use something like PKI to do maybe a more digital lockout tagout, probably as a redundant system and not a replacement. A couple other notes. Again, it only supports Modbus right now. Keep moving on. A couple caveats too, okay? This is not designed to be like a life-saving, tool or anything. Really kind of more for research and understanding the control environments that you are responsible for securing. This is not a substitute for network security monitoring either. You're still going to have to do all the other stuff like segmenting your network and hardening systems and asset inventory. If you're not doing these things already, OT Safe is not for you. If you're taking people on submarine trips to see the Titanic, OT Safe is probably not for you. One of the biggest hurdles, I think, to implementing really safety engineering and detection is that you really need a fundamental understanding of what the system is. And there's always been a gap between, IT practitioners and control system engineers. And we tend to, leave them to their domain that they're responsible for. But we never really peer in and try to understand how things work. And it is complicated. But in order to build a system like this that you can use to detect and prevent unsafe conditions, you are going to have control system operators. Some good news here, there is a regulatory driver that should help compensate for these things. So OSHA has a process safety management standards, or PSM. The two in green are the most important. So you are required to document safe upper and lower limits for items such as flows and pressures and temperatures. And you're also responsible for doing an evaluation of the consequences of deviations. So what happens if something goes wrong, right? Now, typically these things are documented in a spreadsheet somewhere, right? With OT Safe, you can actually operationalize these things and take these in as parameters and again, start building a system that is secure by design and safe by design. A couple more resources, kind of some overlap with some things we're talking about. Consequence-driven cyber-informed engineering, or CCE. This touches on really at their core, both of these, IEC 62443 also, they're really cyber safety frameworks that provide blueprints for securing systems against attackers and accidents, really with the intent of keeping things safe. They are different in their approaches and methodologies and things, but if you're interested in getting into the industry, these are two great resources that you should really consider getting familiar with. There's a big demand for people that are qualified and knowledgeable in these things. The top one was made by INL. The bottom one it's some kind of ISA is the organization, but they're an international organization. and not a lot of adoption yet in the United States. A lot more in Europe and other parts of the world. Cool. So yeah, that's the end. That's my AI-generated QR code. I hope it works. If you're brave enough to scan it, it'll take you to the GitHub repo. Otherwise, you can just type it in and go there. So, thanks for your time.